Welcome to Networking Principles for Medical Devices, layers 1 through 3. Happy that you're here. My name is Mark Orndorff. I'm from Spacelabs. I work as an enterprise integration manager at Spacelabs. I have over 20 years of IT experience. Started out as a system administrator. I've been in various roles along the way: system administration, network administration, database administration, a little bit of development, not a lot. Prior to Spacelabs, I was the director of IT at PAML over in Spokane, Washington, and just recently CISSP certified network security guy. So that's kind of a little bit about my background. What are we going to talk about today? Well, today what I hope to do is cover networking at kind of a basic or a little more than basic level, mostly so that to help as a biomed, somebody working with medical devices, to not only troubleshoot your own stuff, but also be able to answer questions when you're talking to network teams and be able to understand some of the things that people are asking you to do. It can be complicated. It can seem complex. Hopefully we can make it simple today. We're talking about layers 1 through 3. Well, what does that mean? Well, layers 1 through 3 refer to part of the OSI model for network communication. There are 7 layers. I think it was Taco Bell used to have the 7-layer burrito. When I was learning it, that's how I can remember 7 layers. So application, presentation, session, transport, network, data link, physical. There's an acronym that people use if they want to memorize it. All people seem to need Domino's Pizza. That's that way. And there's one going the other way too, but I don't know the other one.
Please do not touch Sally's pet alligator.
There you go. So what is the model? It's a model. That's what's important to remember. It's a model. It's descriptive. It tends to describe what's going on in TCP/IP networking in particular. It provides us a lexicon of terms that we can use when we're discussing things back and forth, so we don't get confused when we're talking to each other. It's a good teaching tool, but on the other hand, there's a lot of gray area in it. Someone will ask a question, well, what layer does this protocol reside in? And the answer is, I don't know. Kind of sits in a couple of them, right? So if you try to fit everything into this box, I'm just telling you, it's not going to work. So but the stuff we're going to talk about today does mostly fit in this box nicely, in these boxes nicely. So that's really good. Oh yeah, I got to remember my animations because they're super important. Okay, so at the end of the day, we have a couple of wonderful. Gotta find the pointer. Oh, no, that's not it. Technology, what did I do? Oh, it's a black screen. There we go. So we got a couple of wonderful, looks like they're XP professional laptops. So those are a few years old. I'm not sure why they put those on there, but say you're going to dig these out, or a current system, and they want to talk to each other. You can think of it as the communication path goes through these layers until it gets to a physical layer on the bottom. And then there's a physical connection with network. And when I say physical, that can be radio, it can be other things, but we'll just call it physical for now because that's what they call it. And then that same information gets processed back up this stack until it finally presents itself to the application. So an application might be your web browser, for instance, right? The web browser, you type in a URL, you're going to go to google.com, you hit enter, that request gets processed through this, gets directed somewhere in Google, gets on a machine in Google, and up it goes through the stack until the web browser says, oh, I know what that is. Someone asked me to serve up a web page, so I'm going to send some information back, process down through the stack, across the physical layers, back up through the stack, and present it to you, where you can see the wonderful Google search box. Okay, I'm going to attempt something else here, and there it worked. So when we think about layer 1, the physical layer, we're thinking about binary voltages or lights or electrical magnetic field. Those are the transport mechanisms. That's what's happening in those. So you have a physical device here that puts a voltage on a port in a hub, and that hub puts that same voltage on another port, and this guy then feeds that up the ladder. We talk about media types when we talk about the physical layer. How is this connection going to happen? And it's concerned with things like sophistication or synchronization. So I want to know the speed that the bits are coming so I know when a bit is there and not there, right? Because if you can think about a voltage maybe being a high voltage for a 1 and a low voltage for 0, if I have 2 1s and 2 0s, is that really 2 1s and 2 0s? Or is it 3? Because it's going to look the same if I don't have some sort of synchronization to that voltage to know when it's going to be there. The device that we tend to think of is, at layer 1, is a hub. We'll talk about hubs in just a minute. That's your typical layer 1 device that only functions really on layer 1. Let's talk about media types. So the most common type of media that you're going to run into is copper. We a lot of times call them by these names. Cat5e is really common, or Cat6 these days. They're twisted pair devices. It's an unshielded twisted pair. So it's just 4 sets of twisted pairs of wires, and they're twisted at a certain rate. And it turns out the more you twist them, the kind of higher up the cat field it goes. The distance is about 100 meters. That's as far as you can go with a single Ethernet cable, and then you got to put something else in there, a hub, a switch, something to kind of send it another 100 meters. Okay? The next thing is fiber. There's a couple different diameters of fiber. They're really small, 50 to 62.5. They basically, instead of using electrical voltage, they send light down the fiber. If you look in the end of them, you'll see a laser. Might be the last thing you see, but you'll see a laser. No, they're not that bright. They run in single mode or multi-mode. So this, I think, is awesome. When people say multi-mode fiber, they basically figured out that, you see that laser light, that it's red? It's kind of red. They figured out if I divide that reddish looking light into different color frequencies, guess what I can do? Instead of sending just one thing down, I can send 3 or 4 or 5 discrete channels down the same fiber at the same time. So I don't know if one of the colors is blue. I don't know what the color is, but I could have blue doing one connection and green another one and yellow doing another one. So that's what multimode is. It multiplexes the colors inside the fiber.
Is there a maximum?
I think it's, I don't know what it is. I think it's 7. I don't know. I think the common is 7. The maximum distance is 2 kilometers for 100 megabits per second. This, I put like a little kind of squiggly equals there. There's a lot of different things we can do with fiber. Depending on the GBIC we choose, we'll talk about that next. The GBIC is really common in fiber. You may buy a device that has a fiber port on it. As you get more sophisticated, devices get more modern, it's likely just going to have a square hole in it. You're like, man, how am I going to get the fiber to go in that? It's just a square hole. Well, they didn't sell you a GBIC. So this GBIC converts, and it can match up with all these. There's different ones for all these different types of connectors. And there's some that are single mode, and there's some that's multi-mode, and there's some that are short run, and there's some that are long distance. So you got to make sure that if you're buying something like this with fiber, you want to make sure you have the right GBIC. You got to have the matching GBICs at each end. So that's GBICs and fiber. The deal with fiber is a piece of glass in the middle of it. It's they drip melted glass down a long tower until it gets really skinny, and then they wind it up at the bottom, and it makes this long single strand of glass, and it's inside the shielding, and so it can be fragile. If you kink it too much, you can break it or cause it so it at least won't transmit fiber, the signal anymore across the fiber. So there's a little bit more. It's not fragile. I mean, if you drop it, it's fine. But if you kink it too tight, you could have issues. So there's some fragility to be considered. The third type of media that we talk about is radio frequency, Wi-Fi, that probably lots of us are using now, or cellular. People are using, we're getting network over cellular. The distance depends. Most of the current, there's several different types. B, G, A, C. You may have heard of N, and those are the kind of versions that have come along as things have progressed. So we're on the versions we're on now are A plus a letter. So AC is the most recent, widely adopted one. It's at 5 gigahertz, and I think it runs a gig. I've got to look. Yeah, it'll go at 1 gigabit per second. So that's the fastest one. What's the distance? Well, it depends. It depends on a lot of things. Is it going through a wall, right? Is there other kinds of radio interference you're having to deal with? All those things can make a difference when it comes to those media types. One of the things is lots of you likely work in facilities where there's lots of these access points, and they all have to play nicely together. And they do that by running on different channels. So, in fact, even your home Wi-Fi, when you turn it on, some of them will just guess at a channel, others would kind of take a look and pick a good channel for you. A lot of them guess. So, if you had two adjacent Wi-Fi hotspots talking on the same channel, what do you think is going to happen? Yeah, it's going to be like a collision. They're going to interfere with each other. You're going to get a noisy signal, and it's going to be half one and half the other. So larger systems today have what's known as a controller, and that controller, it listens to the Wi-Fi hotspots, and they figure out how powerful they should be, and how many, and what channel they should be running on, so they're not interfering with each other. Now, you can get a tool for free, download it at home, and the Wi-Fi analyzer, and just run it at your house if you haven't ever done that. And you'll see all your neighbors' Wi-Fi hotspots, everybody around you there, and you'll see where you are. Odds are a bunch of you are stacked up on the same frequency. Go on your Wi-Fi router and move to one that's empty. See how much better range you get out of your Wi-Fi router. So, but the enterprise systems do that automatically. Or not automatically, but they have tools to do that. Okay, so why would we choose copper over fiber, Wi-Fi over copper, fiber over Wi-Fi? Why do we choose the different things that we choose? Well, obviously there's some advantages and disadvantages of each one. So copper tends to be our commodity media, in the sense that it's cheap. You can buy devices that are really dense in copper ports. They're very common, they're inexpensive. So the backbone of what we do in IT is copper connections, copper Ethernet. Copper though has the limitation in length, right? And we can't multiplex down it. So if I need to get a lot of data across the big distance, I'm probably going to move over to fiber, right? On the other hand, fiber can be more expensive, so I don't typically use it everywhere. There's also the being more prone to damage, right? So if it's being moved around or people are in it, I'm going to move away from fiber. And then Wi-Fi, obviously, if we want to move around, right? Using Wi-Fi. Okay. I don't know, any questions so far? Okay, good. Well, you can speak up if you like. Universal symbol for a hub. I'm just going to cover this briefly. The important thing is hubs receive a volt, and they put that same voltage signal on all the ports. Okay? So if I have two guys talking on a hub, and he's transmitting ones and zeros, those same ones and zeros are going to be on every other port in there. So if there's just two guys talking, that's probably fine because they're kind of coordinating their communication back and forth for the most part. But what do you think is going to happen when I add a third and a fourth guy in there? Remember, every one of those is just going to, whatever they put on the port is going to go on the port. Collisions, right? So what does a collision mean? A collision means that two devices are trying to use the same port at the same time. They're all trying to communicate at the same port. That's a collision. A hub is prone to collisions by its very nature. You're going to have collisions. And they don't do anything about it, typically. Even the most smart hubs typically will just flash a light when they see a collision. So you can watch that you're having collisions, but they don't offer you any remedy for collisions. So this is the 543 rule for hubs. My rule for hubs is 0, 0, 0. So use 0 hubs here, 0 total hubs, 0, 0. And the reason I say that, I'm not just trying to be silly or whatever, is hubs are not very expensive, but switches are not very expensive now either. There used to be a time when a hub was way cheaper than a switch. But I don't even know if you can buy a hub. I haven't tried to buy one in a long time. I think maybe it would be like in a, some sort of historical website of historical network gear. So you could run like your old IBM AT on there. Anyway, but if you're going to use 5 max on a single network for 4 uplinks, interconnections, and only 3 of them with clients. And that rule is to keep the collisions at a manageable level, essentially. But again, follow my rule, it's better, 0, 0, 0. If you're stuck with hubs, minimize them, and we'll move on to something better than that. Okay, bottom line of media, it's the physical layer. All the different media types have pluses and minuses. That layer 1 is just focusing on the physical connection between devices, okay? Voltages. Okay, so talking about the collision thing, how can we do better than that? You can think of a hub as, do any of you here remember a party line? Do you remember? My grandma had one, and you go to pick up the phone and somebody else already talking on the phone, right? Because it was 2 other neighbors and they all shared the same phone line. That's a collision, right? So what did we do in the phone world to solve that? Well, we put in more switchboards, right? So then you would either dial the number. In the old days, you had to tell the operator where to connect you to, but you dial the number, it goes into a switch, and you have a unique connection that's just for you between the two houses. So layer 2 takes us to that level. Layer 2 in the networking. We're going to go to layer 2, and we're going to talk about switching. Okay? So notice that the switch replaces the hub. Right? It takes care of all the voltages, all the synchronization, the electrical signals. It takes care of all that, but it adds this ability to look into the message that's being sent, the information being sent, and determine where it came from and where it's going to, and it only puts that frame on the port where it's going instead of all the ports. Okay? So that's the difference. It reads the frame, only the ports that need it, and it does that by maintaining what we call a MAC address table. Have you guys heard the term MAC address before? Is that familiar to everybody? We're going to talk a little bit about the MAC address. Here's the switch here's the symbol for a switch. So MAC addresses it's a unique address for every piece of hardware, which is kind of amazing if you think about it. Every network port that you have has a unique MAC address, for the most part. There are some exceptions to everything we talk about here, but for the most part. If you want to see it on your laptop, ipconfig /all. So bring them all up, and you'll be able to see the MAC address on your laptop. So it's right here, physical address. It's these 6 numbers, and they're hexadecimal numbers. So hexadecimal numbers. You guys familiar with hexadecimal? Hexadecimal ends at F. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Hexadecimal. Every number, instead of just having 10 values, can have 16. So that's the physical address. That's how you see it on your laptop. Every device has it. When the data link layer 2 that we're talking about, processes information, it processes it into an 802.3 frame. So what is 802.3? 802.3 is the engineering standard for Ethernet. You don't need to know that, and I didn't put it there because I don't know if I remember that. The data is packaged. Here's the data that the layer above passed to layer 2. Layer 2 adds 3 pieces on. It adds the source MAC address, and it adds the destination MAC address. Now, you might ask, well, how does it know where the what the destination MAC address is, right? Because it doesn't know. Well, it broadcasts a request, and that broadcast is called an ARP, A-R-P, Address Resolution Protocol. It says, here's an IP I want to connect to. Who are you? And it broadcasts that, guess what, to every port on the switch again. So for that one little piece of networking, we're back to flooding every port with something. And guess what? The guy that replies broadcasts to every port again. Says, oh, I'm this, and here's my MAC address. So it learns it. The TCP/IP stack, the software on your device learns that MAC address. It also puts in, go back, sorry. It also puts this in right here. This is a checksum. So what a checksum is a checksum is a mathematical function that you can run on a piece of data, and it gives you a value that's unique at the end of the data. I'm not smart enough to know exactly how that works, I'll be honest with you, because it seems like to exactly represent, 32 bits of data, and to keep it be unique, I would need a 32-bit number. But mathematicians will say, no, you don't need that. It should be much shorter. So I don't know how they do it. It's magic to me. But that checksum says, this is what the data looked like when it left here. Okay? So the machine sending the data sends that frame on the port. It's port 5 right here. Guess what the switch does? The switch says, oh, I just got some data from 000D56E48A9D. I'm going to store that in my table so that I know that that's who's sitting at port 5. That's a MAC address cable or table, or an ARP cache, sometimes called an ARP cache. So if some devices you may change a device on a network. You take out, I'm not saying Spacelabs monitors do this, but some competitors might. You take out a monitor and you put in a new monitor. What have you changed on the network? What's different? It's a different MAC address, right? It's a different device, right? Guess what? Until this guy gets something from that device, it doesn't know that you've changed that, and it's not going to know where that is. Sometimes, in more complex networks, those ARP caches can get out of sync, and sometimes you have to do what's known as an ARP flush. You flush the whole ARP table down the drain so it forces the switch to get going and relearn everything. And all switches do that on a regular interval anyways, but we don't want to wait around for it to do that sometimes, so the network guy will run ARP flush and destroy the ARP table so it rebuilds. Okay? So it knows from some traffic earlier that this A9 guy was on this port, so it takes that frame and it puts it on that port, and it gives it to that guy, and that guy pushes it back up the OSI module until it gets to the application. Does that make sense? Any questions on that? Okay. Two major categories of switches, unmanaged and managed. If you go on, Amazon or the vendor of your choice and buy a little 5-port switch for your home, it's going to likely be unmanaged. You can't log on to it. There's nothing to do on it. It just sits there and switches. It doesn't have a lot of brains to it. If you're working in a network environment, you're definitely going to be using managed switches. They both do the same two functions, or the same function, it being they forward packets and they capture MAC addresses. Managed switches give us a lot of additional features, but the ones we're going to talk about today are VLANs and spanning tree protocol that are important for managed switches, for switching. Okay. Have you guys worked with VLANs? You guys heard that term and what you do? Raise of hands? Okay, so we'll talk about it a little bit. VLANs are awesome, but they can confuse you sometimes. So this is like the modern day workhorse of every data center. I don't think I've ever been in a data center, well, maybe one or two, but almost every enterprise has, large enterprise has, but one of these switches somewhere. And lots of them have lots of them. This is a layer 2 switch. Now you'll hear layer 2 switch and you'll hear layer 3 switch. At the end of this, at the end of our workshop today, I hope you'll know the difference when somebody talks to you about a layer 3 switch. So multiple VLANs, spanning tree, and it does a thing called trunking as well that we're going to talk about. Okay, so here's some people are all talking in the same room. They're each having their own conversation. This is a network, and let's say it's even a switched network. Okay, they're not colliding with each other, but they're all there, and the room is kind of noisy. Remember all those broadcasts I told you about, the ARP requests and the response? They're going everywhere, right? It's fine if you have a couple hundred machines maybe, but when you have a couple thousand, it starts to become a problem because you spend a lot of time on those broadcasts, okay? It's also fine if it's okay that kind of everybody's traffic is all a little bit intermingled. So imagine in your organization, you may have a wing where there's medical devices, and then across the hall and the other way, there is a Wi-Fi hotspot for your patients and people in the waiting room to use. From a security standpoint, I'm not going to want that traffic on the same network because one of it's highly secure and the other one, who knows what's going to happen on that network, right? So there are reasons we want to separate these out. So we can build rooms around them, and we do that through VLANs in a lot of cases. In VLAN, I can take that switch that I just showed you, and I can carve it up so it kind of looks like a bunch of little switches, virtual LANs. So I can take 5 ports and put it to LAN 1. I can take 10 and put it in LAN 2. I can carve that all up. And if I plug something in one that's in VLAN 1 and I plug something that's in VLAN 2, there's no way for those to talk. They're completely segregated. Okay? So that's what we've done here, right? We've isolated these conversations, so now it's easier to have the conversation, right? But at the end of the day, they want separation, but we also want the ability to communicate back and forth through these networks. So we're going to put some doors in as well. We'll talk about that in a minute. Okay, so start up here, ignore this down here for now. Remember, we had that frame before, and I forgot to put the checksum on this, but it's there still. We have that frame. When we want to use a VLAN, the layer 2 just puts a VLAN tag, and it just labels it. This is VLAN 20, right? So then the switch knows I'm only going to forward that frame to ports that are joined into VLAN 20. That's the only ones who would ever get this. I would never send it to anywhere else. So it's done within that switch, right? So the interesting thing is I can carve up a couple VLANs here, right? And people, this is how it works in IT. Like you say, hey, there's this really neat thing we can do. And they're like, oh yeah, but can you do it different? Sure, yeah, we'll do that too. So we can take another switch and we can carve it into network A and B as well. So I can have network A, B here, and I could join them together by running a cable between A, right, and B and B. Do you see how I join those networks together now? And now I have A on both places and B in both places. And this is done all the time, all the time. If you look at a switch in your typical access layer in the closet, you're going to have multiple VLANs sitting on that switch. One's going to be for your devices.
So that's a physical connection between the two? It's not software?
Yeah, what I've done, just put together is a physical connection with 2 cables, right? One for A and one for B. But we can do better than that, and I'll show you that in just a minute. But the important thing is that network. So I can make a VLAN that's the biomedical device VLAN. And some of you probably have that, right? And I can propagate that VLAN out to access layer switches all over my hospital or all over my facility, right? And then I get on that switch, I can say just ports 2 and 3 are in the medical device VLAN. And then I can plug those into the ports that go to the room where I have the medical devices. So I can deliver that VLAN all over the place. Well, obviously, if I've got 10 of these VLANs, I don't want to run 10 cables between those two switches. One, it burns up 10 ports on the switch. Two, it's a lot of cable pulling to do. So what they do is we do what's called trunking. And because there's this tag on this, I can run traffic from multiple VLANs all down the same trunk connection. Right? So I just have to open up that VLAN on that trunk. I make a trunk connection, it directly connects the switches, I tell it which VLANs are allowed. And now I can do it with one cable instead of 5 or 6, okay? So someone might say to you, because I'm on these conversations, it wasn't working right, and then the network guy comes back on, and they're like, oh yeah, the VLAN wasn't on the trunk. I don't know if you guys ever heard that before, but that's what they'll say. You're like, what? The VLAN isn't on the trunk? Now we know what that means, right? That trunk line right there wasn't authorized to deliver that VLAN out. Or they'll say, yeah, it didn't work because I didn't have the VLAN on the switch, or I didn't have the port in the VLAN, right? So the VLAN has to be on the trunk, on the switch, and the port has to be a member in the VLAN. Okay. Any more questions on that? VLANs are great. From a security standpoint, we love them. We like you to subdivide your stuff up because it keeps problems from moving from one area to the next. Okay, so this just kind of, I didn't build this slide, like somebody gave it to me, and I didn't know what the moving around stuff was, so I'll just get through that. Okay, the next thing we talk about, spanning tree protocol. So what spanning tree does is it lets you have redundant links between two switches. Remember I showed you those two switches and they're connected with one wire? Inevitably, the second I connect those up and I say, hey look, I got the trunk going, I got the VLANs running out there, it's awesome. The guy's like, well what happens if something happens to that cable? Oh yeah, I gotta do something else. So I'm gonna add another trunk, right? I'll just add 2. Or I'll run it another way, I'll run it through another provider, I'll do all kinds of things to make it resilient, but that can create problems. So spanning tree helps fix those. Spanning tree is by default on every port because it protects us from big problems. It removes loops at layer 2. So here's the thing I talked to you about, right? I just built my awesome network. It's going to these 3 switches. You know, I got floor 1, floor 2, floor 3. Everybody's cooking along. And then somebody says, well, you know, if that switch on floor 2 dies, now I can't communicate between floor 1 and we're down for 2/3 of the hospital. That's a problem. Like, oh yeah, I know what I'll do. I'll just connect that, right? So you can see now that switch B is gone, I can still connect A to C, right? Which seems great. It is great. But this is what's going to happen. One of those nodes, they're all going to do it, but we'll just show you one. One of them is going to send a host packet out. The way switching works, switch A is going to send it to B and C. Then guess what happens? B and C send it to each other, and then guess what they do? Oh yeah, back to A. A's like, oh yeah, here's a packet. I better send it to B and C again. Okay? Uh-oh. Over and over again. This is a broadcast storm. So you may have heard that. Somebody said your network went completely to its knees. Everything stopped working. They're like, oh, there was a broadcast storm. Right? So these guys back here, his broadcast packet, because everybody's broadcasting, as soon as he broadcasts, it says, oh yeah, all ports, all switches. Right? And it just keeps going. Now, one of the things that we have in TCP/IP is we have what's called a TTL, time to live, on a packet, right? So every time that packet kind of hops around, it like increments down. And then when it gets to 0, whoever gets it to 0 throws it away. So it's designed to help bad routing, because it's at the IP level, which is on layer 3. It doesn't work at layer 2. Okay? So we're going to show you, there's a simulation here. I think we're going to run it, I got to get there it is. Technology, you know. It's like, you know, I can build a network, but can't operate the copier. Okay, there we go. All right, so thank goodness for YouTube. Oh, there it goes. Yeah. So there's, I paused it. Okay. So there it is. You saw the first messages going out. They're hitting a switch. And now this guy is not going to throw things away. He's going to keep replicating. And you can see different versions of things going out. And now all of a sudden, oh, wow, everything's getting slow. Hey, the monitoring stopped working. And pretty soon it's so full that all of your interfaces are completely saturated and nothing's happening except for forwarding those broadcast packets around. It's a bad thing. So I had it happen one time at a network that I was working on, and we fought it for, we could kind of get it under control, then it'd come right back.
We're going to talk about workspace, so for those of you who have been to some of my sessions, there will be no Chuck Norris jokes this time.
That's good to
That
hear.
happens tomorrow and Thursday, but not in this session. These guys aren't Chuck Norris fans, so you can go on
Okay.
what. But we're going to talk about the workspace, and we're going to get a little bit.
No, I don't think we'll talk about that, just for fun. We'll tell my story, it's much interesting. We couldn't figure it out all day. We finally started sniffing around. We got it out, figured out kind of a source by trying to kill everything and watching it respawn and see where traffic would follow first. It took a long time. We finally got it out to the PC Tech's workstation. He had put a little hub on the network, and he had taken the plug that was going out of one, and I guess he unplugged it from, he had, cords everywhere, and he thought he was plugging it in, and he took one that was coming out and just plugged it back into the switch. That was it. Took the whole corporate network down. So we don't want that to happen. So I don't know why that's there. Let's go back here. So what does spanning tree do? This is what spanning tree does. Spanning tree, by default, will take a look at these paths, and it says, these are going to the same place. That's not good. So I'm going to shut one of them down. So it'll just shut one side down. And I'll do that anytime it sees a redundant connection. If it doesn't shut it down permanently, it kind of waits and monitors and checks. Then if for whatever reason this one goes offline, it'll bring that back up. That's what spanning tree does. Okay? It keeps us from getting into trouble. So it's really important on the network. We'll go past that. Okay, here's some of the stuff we talked about. We talked about a frame. A frame is the fundamental unit, layer 2. We talked about MAC address. Layer 2 is the data link layer. We talked about spanning tree. We talked about VLANs. And we talked about trunks, and all this is run on Ethernet. So I think we covered that. All right, layer 3. Let me check my time. Okay, I got lots of time. That's good. Layer 3 is where in layer 2, we made a network, right? We made a network. We got stuff to talk together, right? And layer 3 is about letting networks communicate with each other, different networks. Does that make sense? So I got network A over here, or VLAN A, and VLAN B, and then I have VLAN C, let's say that's the data center. Both those probably need to talk to the data center. So we're making those networks communicate with each other. That's layer 3. And layer 3 is where you introduce IP addresses. You notice I haven't talked about IP addresses hardly at all. The only time they're really used concerning layer 2 is when you're trying to determine ARP, because that's all you have is the IP address. We're talking about routing. When people talk about a routing, that's layer 3. Okay? When people were talking about packets, so in layer 2 we're talking about frames. Now we're going to introduce a packet, which is built on the frame concept. And what layer 3 really gets us is the scalability that allows network communication across the world, right? The ability to route between different networks. Okay, so so notice it works with the switch. Switching and routing work together. Okay, there's a symbol for a layer 3 switch. That was going to be my question. So we talked about a layer 2 switch. Now we bring the notion of a router, which is a standalone layer 3 device, and a layer 3 switch. Who can guess what a layer 3 switch does that a layer 2 switch doesn't do? Close. can route between different networks, right? A layer 3 switch brings a lot of the functionality of a router into the switch. So Cisco 3600 series switches are layer 3 switches. They give us a lot of that functionality, which gives us a lot of flexibility. So here's a packet. Here, remember, here's my frame stuff. Here's my frame stuff here. The routing, I'm just going to put a source IP address and a destination IP address. Okay? And the reason for that is I can't possibly know the MAC address of every device on the internet. And there's not a good way of delivering that across the whole internet, right? I mean, you would have to keep a huge MAC table, right, or ARP cache. So we use IP addresses. They're the way we address on the internet. Okay, so here's the things that you've probably seen when you're configuring stuff. An IP address, a subnet mask, which we'll talk about, and a gateway. All right. So those are the elements. Okay. So when we see any numbers on a computer, they're not stored in decimal anywhere on a computer because a computer only knows ones and zeros. Everybody knows that, right? So when we see a regular IP address, 192.168.100.111, this is how the computer sees that. There's a series of zeros and ones. So this is, in decimal, you have the tens, or the ones, the tens, and the hundreds columns. In binary, we have the ones, the twos, the fours, the eights, the 16s, the 32, the 64, and the 128s, and they keep going. This is an 8-bit binary number. 8-bit binary number is called an octet. And IP addresses are made up of 4 octets. Okay? So you can kind of see that if I take 128 and I add 64 to it, I'm going to get 192, right? I think so. I added it a few times before I came. It works. Right. So 100, right? I'm taking a 64, a 32, and a 8. And I add all that up, I get 100. Okay. So what we tend to call them octets. So a network or an IP address is made of 2 parts. It looks like it's made of 4 parts, but it's actually 2 parts. And the 4 parts are the network address and the host address. And you can think of the network address as like the street and the host address as the house number, right? Some streets are really small and have a couple houses on them. Some streets run for miles and they have a couple hundred houses on them, right? Same with networks. Some are small with just a couple hosts, some are big. We get the ability to kind of change which portion of this is the host portion and which is the network portion. So the maximum number here, I don't know if we talked about this, but what's the highest this number will ever be? 255, which is 260 or 256 values, 0 to 255, right? Those are the values. So if I put a dividing line here and I say this is for hosts and this is for networks, how many hosts can I have? 255, 256, but it's 255 because there's a reserved address for 2. That's 255, 254, 256, somewhere in there. But yes, we'll call it 256. Okay? That's the most I can have on any one network. That's not always going to work for everybody, right? So what that would mean is I could have a bunch of networks with 255 on them, and I'd have to provide routing between each of those. Well, routing costs more than switching. So I'd rather switch more if I can. So guess what? I can move the line. I can just define a network that has more hosts in it by moving the point that I changed over. Now what do I have? I have 255 for each of these 255 networks. Somebody tell me how many that is. 255 squared. Excellent. It's an excellent math answer. I love it. What's the value of pi? 22 sevenths. Yep, exactly right. Okay, so it's a big number, right? It's a really, really large number all of a sudden. So just while I'm here, I want to point out that this is a huge gap in numbers between here and there. Like, this is getting too big, this is too small. So we need to be able to put this line kind of in between here too, and we can do that. But it doesn't look really good in decimal. Like, if I just divide the number 100 in half, that doesn't really, you can't have half a zero there. It looks great in binary. You can totally see it in binary. So we're going to go over to binary, okay? Okay, so here's our binary. We use to define which part is the network and which part is the host. We use the subnet mask. That's what it does. It masks the address. It masks off one part or the other. So if I take that 255, this is probably the most common subnet mask that you guys see the most, right? Like, that's the lazy one. It's like, okay, it's a 10 network, and it's 255, 255, I don't want to think about it that much, so that's fine. You can have 250 hosts even though you only have 3 monitors, right? Because it's 10 network and I have a gajillion of them. So that's what they tend to do. But you can see that these are all ones, right? The max value all the way till here, and these are all zeros. Well, when I take that, I can do a mathematical function, an AND function, and I can mask off. See, here's my address. Here's 119 in binary, and I mask it off. If I use the AND function, I get just the network portion. So I know what the network is. If I use, I think it's the OR. I have to calculate it, figure it out and see. There's another function I'm going to use, XOR or something. I don't know what it is. And I'm going to get the inverse. I'm going to get just the host piece. So what does it do? What does a subnet mask do? The primary thing it does is it tells us if an address is on our local network or someplace else. That's the most important thing it does. Because we need to know that for layer 3 to work properly. If it's local, if it's on my LAN, if it's in my VLAN that's already defined, do I need layer 3? No, because remember in layer 2, we had traffic going back and forth just using layer 2. I don't even need layer 3. If it's someplace else, I can't get there without layer 3, right? So your host has to determine that. So it needs to know the subnet mask, to know what's on the network and what's not on the network. Does that make sense? Any questions about that? Okay. I will say this. There are many ways of describing subnet masking. This is the only one that makes sense to me. And it may not be 1,000% accurate, but it's 99.99999. I mean, there might be someone who has an esoteric reason why that's not the right way to explain it, but I can't understand that way of explaining it. So I look at it this way, and it always works for me. Okay? That is what it's doing. That's how it's working. So what do we do if the IP address isn't local? This is my favorite answer. I like this, like the ultimate slacker answer. I give it to somebody else. It's their problem, right? And in networking, we don't even really need to know for sure that who we're giving it to, we don't need to know the whole rest of the way. We just need to know the next hop to give it to, right? So we need to know where it's going to go next. And guess how we do that? We do that through what's called a routing table. Every device has a routing table. This is off my laptop, okay? I put some fake networks on it yesterday, and I printed it off. And it looks ugly, but we have a network destination. This is some place that you might be trying to get. This is the net mask of that destination. So remember, the two things that define my network are the network address and the net mask. So I know which part of that network address is the network. I need to know that to know how to find that network. Okay? So that defines it. Then the gateway tells me how to get there, essentially, and which interface is going to get me there. Okay? And then this metric tells me if there are two of these that are kind of have the same, they match on two things, this tells me kind of how expensive I think it is to get there. So it helps me choose which one to use, essentially. Typically, if you print off the routing table on your Windows machine, your stuff's going to start at the bottom of this, and it's going to work through until it finds a match, and there it goes. It's going to use that to route. Okay? So, if I'm trying to get to, let's see, what's the network I want to get to? If I want to get to this network right here, 172.29.4, right? This is, I have this interface on my machine. That's not the same network. And I have this interface on my machine. Let's see, yeah. This one here, 10.27.77. Oh, by the way, you can ignore all these 127.00s. Who knows what that address is? It's called the internal loopback. It's how the machine knows itself. So anytime you see 127.00, it's called home. So like there's like a funny shirt that network guys wear. It says like something about home in 127. Places that I don't remember how it goes. Anyway, so those are all loopback. So do not worry about those. But if I'm trying to get to something, I got a packet that's going to say 172.29.4.16, right? I'm going to go down here and I'm going to say, ooh, look, there's a route, and that matches, right? Because see the mask? I know that it's all the 4s, because I know it's a 255. Any of these numbers on this are going to be okay. It's going to be in that network. And then it says, okay, here's the next hop. Notice the next hop isn't the one I'm looking for. It's one that it's learned that that's how I can get it there somehow. And it doesn't know, my machine doesn't know how it gets there after that point. It just knows if I give it to George, he gets it to Andy somehow. And I don't ask questions, right? So I put it on that one and I give it to George. Okay, so why am I telling you all this? When I get down to the bottom, I have this special net mask. From what we know about net mask, what does this mean? 0, 0, 0. It's a weird net mask, right? It's no value. It means anything goes, right? So this is your default gateway. Going to anywhere, 0, 0, 0, 0, 0, 0. If you haven't matched to this point, I want you to send it to the default gateway, which was configured when I configured the device, I put in 192.168.0.1. Does that make sense? Any questions on that? That's how routing works on a device. So if you have a device that never needs to get outside of its network, say you have a LAN and you're going to put a monitor on it over here, and you're going to put a nurse's central station over here to monitor that remotely, and that's all they're going to do we need a default gateway? We don't, because they're on the same LAN, right? They can communicate layer 2 and they'll be just fine. Don't need to put it on there. What if you have 2 interfaces on a device and you put in 2 default gateways? I can tell you, that's not good. So, and you can do that on a Windows machine. So you want to be careful if you ever have to configure a second NIC, just 1 default gateway. Okay? Because it's undefined. It's like dividing by 0 in the networking world. Okay, it won't kill things, but it just won't work right. It'll look like it's working right, and then one day it won't work right. Trust me. Not that I've ever made that mistake, but just trust me. Okay. All right. That's how routing. That's how it works essentially. And I just want to go through. I want to see what we're covering here. I'm going to go skip forward a couple steps here. All right. I want to go back here and cover something that's maybe a little out of order. I could just go over there and find the correct one, but I think I'm 1, 2 away. Okay, if it's not this one, then it's not that one. All right, well, okay. So when we're delivering network traffic, and we get a piece, the stack gets it, it gets down to a certain point, the first thing it has to figure out is whether it's local network or it's not. If it's local network, it builds that frame and puts it on the wire. But if it doesn't know the destination MAC address before it puts it on the wire, because it can't put in there, it doesn't ARP. If you put a sniffer on a network, you'll see those ARP requests. It doesn't ARP, it asks who is 10.21.15.5, and then someone responds, so it puts that in there, it puts it on the network, sends it to the switch, and what does the switch do? If it's a hub, it would broadcast it to all the ports. But a switch is different. A switch knows which port it belongs to, and it only puts it on that port, right? That's layer 2. It's in the same network. Now I have something come in, and I'm on the 10 network, and this is on 178.68. something or other, and I'm looking at that, and I say, that's not local. So what do? I take the frame, I put in the source and destination IPs, and that makes it a packet. Now it's a packet. Okay? That magically it makes it a packet. I then, what do? I then look at my routing table, and I say, do I have a route that gets me to this address? And I cruise through, nope. I get all the way to the bottom, and what route am I at? Whenever at the top, the last one, what am I going to be? 000, the default route. And so I'm going to put the destination in my packet as 0000, and I'm going to, no, I'm not going to do that, I lied. I'm going to leave the IP addresses the same. I'm going to put the MAC address of the default router on the frame, and I'm going to send it to the router, right? The IP address isn't going to change, okay? So it does tell you something about the default gateway. If I'm going to send that to the default gateway, what layer am I doing that at? Is that 3 or is that 2? 2. How do we know it was 2? Yes, the default layer, I'm going to get to that. The default gateway has to be on the same LAN. But we knew it was layer 2 because the way I got it there was by putting the MAC address in. That's layer 2, right? So that's the communication there. The whole communication to the endpoint is layer 3 because it's based on IP. But that little hop to the next hop is a layer 2 hop, right? The whole thing is layer 3. So the router gets that and says, oh, here's something. Wow, is this? I'm looking at the IP address now, and I'm going to go through my routing table. Is there anything on here that no. And guess what it does if it doesn't have a route? Default gateway. Somebody he knows how to get to layer 2. He gets the MAC address, takes the other destination out, puts the new one in, sends it down the pipe. Puts his MAC address in as the sender. Right? They keep doing that. Next hop, till finally someone's like, oh, I have that route local. So I'm going to put the destination MAC address on there, and I'm going to send it down, and it's going to get to the host. Does that make sense? So all the way along, they're just looking at the frame, finding the next hop, and passing it down. Yeah? It does. Yep. So you might see in the error on a switch, cyclic redundancy check failed, CRC. That means that you had a corruption in the broadcast, in the transmission of that. So if you're getting that, you're going to check your cables. You're going to check your media. Make sure that it's good. It's typically cables. Okay, everybody understand that? Did that answer any questions for anybody? So that's how that works. Then there's going to be a response back. It's going to do the same thing going back. So it gets through. Okay. Let's spend like 5 minutes to get back up to where we should be here. This is just a quick review for you guys. Scan that in. Okay, oh yeah, this is good right here. Okay, let me check time, how we're doing on time. Okay, we got about 15 minutes, right? I got it. Okay, private IP addresses. Have you ever heard someone say, oh, the sky's falling, we're running out of IP addresses? No, maybe not, but people say it. And there is a limited number of IP addresses, right? There's a maximum. We got from 0000 to 255.255.255.255, and that's all there are. At first, people were really worried we're going to run out. In fact, we invented a new version of IP called IP version 6 to address the problem. But every year that I've been in IT, IP version 6 happening in 2 years. And it just keeps happening in 2 years. I'm not sure. We'll see. It's in here. It says it's coming. And I could have put it in 5 years ago, and it's probably going to come at some point. But it's not here yet for most of us. So what they did, though, is they carved out big chunks. And you look at this. This is a huge range. I don't know what that number is, 255 to the third. That's a huge chunk. And these are private IP addresses. So if you put a packet destined for one of these IP addresses, send it to your internet provider and say route this along, it's going to be, nope, I don't route that packet, that's private. So the internet won't route these packets at all. I can guarantee, almost guarantee, if you go to work and look on your PC at the IP address, it's going to be in one of these three ranges. A lot of people use 10, a lot of people use 172. Anything you buy from a box store and plug it in, 192.168.0.1 or .1. Right? It's private. So the idea is everybody gets these internally, and you only use a few real ones on the outside. And that's how it works. We use a magical technique called NAT, Network Address Translation, that basically there's a gateway there. It takes your packet, it knows who you are, it builds a table of where it came from, where it's going to. This is in a different layer, so I won't go into too great detail. But it keeps track that you're talking to somebody on the outside, and it assigns you one of its valid IP addresses to respond to. Then when that packet comes back in, it's like, oh yeah, I know where that goes. I'm going to send it to that guy. Okay? So effectively what it does is it gives us all these. You can use these in your house. Like if you want to build a huge network of this size in your house, start collecting all your friends' old PCs and old switches and stuff, go at it. They're all yours. Anybody can use them, but they won't route on the internet. Okay? So Class A, a Class A network is a network of this size with a net mask of 255.0.0.0. The networks that are out there assigned to companies, the real routable ones, they're assigned to companies. And like Class A's, only the big guys have those. Like Department of Defense has quite a few because they invented it all. I mean, HP has one. HP got theirs by buying DEC. That's how they got theirs. So there's a few that have these. Class B's, they're two. They're smaller networks. You can see they have fewer hosts in each one. And then Class C's. And these ranges, there's a whole range of Class B's, Class C's, Class C's. Me personally, I don't get caught up on that labeling of classes too much. It never really has any practical use. It's on every network test I've ever taken ever. But I've never used it once in like the real world, whether it's a Class A or Class B or Class C. Because we don't mask that way. People will take this Class A and they'll mask it all the way down. You probably have it at your organization. There's a 10.21.15.0 network. Okay? All right. Types of IP traffic. Now this is getting, so I'll just say, we've covered layer 1, 2, and 3. Some of this stuff now is getting into different layers, but it's stuff that people ask about that we just want to cover a little bit. Types of IP traffic. Point-to-point. Point-to-point is one person. Unicast is what it's called. Point-to-point, one computer talking to one. Multicast, one computer talking to many. Broadcast, you could think of, where do broadcasts come from? A radio tower, right? Or a TV tower. If you want to watch Channel 4, what do? You turn your TV to Channel 4, and you get the content on Channel 4. That's what multicast, no, I got it backwards, sorry. That's multicast. Broadcast is everything. We talked about that. I don't know why I was backwards on that. Multicast is the one-to-many, where there's one guy and there are a bunch of people looking at the same feed. So just going through Unicast point-to-point, broadcast, see everybody's getting it. We don't like that traffic in network world very much. And then multicast. So in this multicast diagram, these two hosts down here at the bottom have decided to, for lack of a better word, subscribe to a multicast feed. And they all get the same thing. Spacelabs monitoring, we use multicast. Multiple devices can monitor one bedside device. IP version 6, when it comes, virtually eliminates broadcasting. And it's all multicast. All the messaging, all those messages I talked about, ARP and all that, is all done multicast. So the nice thing is if you don't want to participate, you don't have to. You can just say, I'm not interested in that. So that's good. All right, layer 3 terms. We talked about gateway, default gateway. Gateway and router are synonymous. The same term, right? A router is a gateway. IP address we talked about. We talked about packet being that frame with the addition of IP addresses in it, right? We talked about the multi-layer switch, layer 3 switch, which does the switching, but it also has the routing in it, switching and routing. We didn't talk about firewall. We'll talk a little bit about these two real quick. Talked about router. We talked about layer 3 switch. Firewall. I think everybody kind of knows what a firewall is, but firewall essentially is what's going to block certain traffic from coming through. And it does that based on a lot of things. The simplest ones do it based on the IP, source and destination IP address, and the port. We haven't talked about ports. Ports is the next layer up. Ports let us distinguish between, say, HTML traffic and traffic from a SQL server. So you can have the same IP address, you could have a SQL server running on it and a web server. And by looking at the port of the data coming in, that machine can tell, oh, that's bound for the SQL server. Oh, and this one's going to the web server. That's what ports kind of do, right? So firewalls, they let us say, I'm going to let all HTML traffic go out, right? Because I'll let my people do what they want. But I'm going to let all web stuff come back. But I think I'm going to block off China because I'm concerned about the security. So that might be a DoD thing to do, right? Or I'm going to block off a certain range because I'm seeing strange activity from that range. I'm going to block off that firewall. You may hear ACLs, access control list, which is kind of the same kind of thing. Some firewalls look deeper and they know the language. DHCP. DHCP is a protocol that runs, it's a service that runs on the network, and it allows a machine to get an IP address assigned automatically. So you guys probably know that, right? If you ever configure an IP, you can choose DHCP or manually assign. DHCP, it's a broadcast, because there's no IP at that point. The DHCP server has to either be on the local network or have a helper on the network. And they send out a layer 2 broadcast that says, I need an IP. Is there any DHCP servers out there? DHCP server does, yep, I got one, here's one, take that. And the machine configures itself as per IP. So DHCP works. Any questions on anything that we covered? That's good. I must be doing an amazing job, or people are really ready for lunch. This is better than after lunch, so I just gotta say. After lunch, you'd be asleep. That's not good. So here's IP version 6. This is just kind of interesting. Okay, what can you tell me about looking at that? What kind of numbers are those? Hexadecimals, right? If somebody says, look at my neat number and it's got a letter in it, then it's probably hexadecimal. And if none of the letters are further along the alphabet than F, it's probably reasonable to think it's hexadecimal. So look at 1, 2, 3, 4, 5, 6, 7, 8. 8 hexadecimal, 4-digit hexadecimal numbers. A hexadecimal number, each of those is 8 bits, right? So that's a lot of hosts, a lot of networks. Yeah.
The second two from now, yeah, why should we pick?
That's a great question. IP version 6 lets you just squish zeros out of the equation, which I don't know if it makes it easier or not, but it does.
So it have to be a leading.
Yeah, see that one's there.
0, 1, 0, 2.
Yep. Yeah, and we do that in version 4 too. Like it'll be 10.1, not 10.0, 0, 0, 1, or 0.
That's numerical, bro.
Yeah.
Yeah.
Yep, that's why you can do that. Okay? So if you see IP addresses like that, you might see them someplace, you're like, okay, I know what that is, that's IP version 6, and nobody's really using that yet, but some people may. Anybody using version 6? They're aware? Okay. I rest my case on that one. Okay. A lot of devices don't support it, some do. Single broadcast domain, multicast instead of broadcasting. Single broadcast domains are gone. It is something you kind of need to have your eye on. Make sure that you understand what your IT department's getting ready to do with IP version 6. You need to have them show up one day and say, we're version 6 next week, and half your devices won't do it, you know. So that's something to consider. Just real quick, this is a common architecture. There's kind of some core routing, and then there's all this redundancy to other routes in the organization. And we've learned today how, particularly in switching, when we have that redundancy, spanning tree is our friend. It can help us. Sometimes it makes mistakes, and sometimes you need a network person to go on there, like, for some reason, spanning tree had that shut down, and kind of reset spanning tree, and everything came up right. But it is our friend. It's really common, too, to have a core, and then this distributions, this is data distribution, and then you have access layer switches attached to this. It's all combined in there. That's the most common you see today. More and more, we're starting to see firewalls between these sections of these segments when security gets high. They don't want the data center. They want to control all traffic going in and out of the data center, for instance. They want to isolate it. So if somebody brings a virus in the access layer, you can't get into the data center. I don't think we're going to talk about this. I think we're going to skip through this stuff. So this is just watchdog timers. This is not really network related. I got these slides from another person as well. So I don't think we're going to cover that today. I will go to this slide. This is good. It's really basic. It's the A+ certification, CompTIA A+. It gives you a good broad coverage, and they just updated it so it's better. It used to spend a lot of time on things like interrupts and hardware stuff that nobody even does anymore. Now we just build hardware to turn on. But it's really good. It's worth it. Come by and see us. We have all new stuff in our exhibit. We have a new central station, new telemetry. That's a really cool Cube Mini. We'd love to see you out. And thank you so much for sitting with me today. I appreciate you guys listening. I hope you walk away with a better understanding. I appreciate it. Thanks.